lot of things that we've already looked at. Um, it's actually going to go back over those, and then it's going to bring in uh, some of the new questions now that we've been studying gases. So what I have here is the equation showing, you tell me, HC2H3O2 in water. Who said acetic acid? That's right, that is hydrogen and acetate or acetic acid. And this is sodium bicarbonate, better known as baking soda. And this is one of those reactions that they show us examples of where an acid reacts with a basic salt, a type of carbonate, so that we get a neutralization. And not only do we have a neutralization, we get a new salt formed, which is sodium acetate. You take the cation from your basic salt over here and the conjugate base of the acid, which is the acetate part, and that gives us sodium acetate. We're going to take the hydrogen from the acid. We're going to take the hydrogen and one of the three oxygens from the bicarbonate to make water, because all acid-base reactions produce water and some kind of salt. And then what's left over is the carbon and the other two oxygens, and that's released as carbon dioxide gas. Since it's a gas, we'll get to use some of our gas law knowledge on it. All right. Then what I've said here is that we're using 500 milliliters of 1 molar acetic acid solution, so we get to work on our understanding of molarity, although fairly simple since I made it 1 molar. We're going to have to do some stoichiometry. And for starters, we need to make sure the equation is balanced, and I think you can probably see already that it is. This C2H3O2, this acetate, ended up over here on the product side intact, still acetate. It's now with sodium, which came from here. All right, so 1 sodium here, 1 sodium here, 1 acetate here, 1 acetate here. Now, this hydrogen, and one of these three oxygens gave us the water, and then the carbon and the other two oxygens makes the carbon dioxide. So everything's already balanced here. The coefficients are all implied. There's a 1 here, a 1 here, a 1 here, and so on. So a problem like this might read this way. It might say 25 grams of solid sodium bicarbonate, 25 grams of solid sodium bicarbonate are added to 500 milliliters of 1 molar acetic acid. And it would need to go on and say this is placed into a 2-liter container and immediately capped off. Okay. So the question then becomes, since one of the products is a gas, what will the pressure be inside that 2-liter bottle? Because as we build up this gas, the pressure is going to increase. Then when I started to write this down, I was at first thinking of just doing this in an open container so that this carbon dioxide could just escape. And for that reason, I had written down a room temperature, and I know that's kind of an odd number, but there's a reason for it. You'll see in a minute. And I had said, well, let's go with a realistic pressure, and I actually pulled out my phone and looked at the current barometric pressure. It's 29.81. Then I said, no, I'm not going to do it that way. I'm going to do this in a closed 2-liter container, so I marked through that. But then I thought about, well, let's talk about the density of CO2 versus the density out in the open, so we will come back and use that number. So we're doing several problems at once here. Hope that doesn't confuse you too bad. All right, so the first thing to do, we know that for 1 mole of this, we need 1 mole of this. So let's see how many we actually have and see if they're in a 1-to-1 ratio. First, what does 1 molar mean? Now, that is something you need to understand and should be able to answer. Remember that molarity, where can I put this? Molarity equals moles per liter. Okay? So when we say that something is 1 molar, we mean there is 1 mole in every liter. Do we have a liter of it? No. We only have 500 milliliters. How many liters is 500 milliliters? Now, this is a type of conversion you're going to do over and over and over this year, so learn how. Remember, 500 milliliters means 500 thousandths of a liter. And 500 thousandths is half of a liter, 0.5 liters. Okay, you with me so far? Now, 1 molar means that there is 1 mole in every liter. So how many moles would there be in half of a liter? If there's 1 molar, means 1 mole in every 1 liter, then how many moles are there in 0.5 liters? Because that is 500 milliliters. Well, it should be blatantly obvious 1 over 1 equals what over 0.5, but if it's not blatantly obvious to you, you can put an x here and you can cross multiply and solve for x. You're going to get x equals 0.5 moles. So when we have 500 milliliters of 1 molar acetic acid, we have 0.5 moles. Okay? If you didn't catch it, rewind it. Watch that part again. Now let's move to our sodium bicarbonate. We have 25 grams of it. What would 1 mole of it weigh? Well, we can go through, and I'm just going to do this quick and rough with whole numbers. Sodium weighs 23. Hydrogen weighs 1. That makes 24. Carbon weighs 12. That makes 36. And 3 oxygens at 16 each would weigh 48. 36 plus 48 makes 84. So we have 25 grams out of a possible 84 grams per mole. And that turns into 25 divided by 84, 0.2976. So I'm just going to round that off to 0.3 moles. Okay. Now, if we have 1 mole of this, we need 1 mole of this to go with it. If we had 5 moles of this, we would need 5 moles of this to go with it. If we had 10 moles of this, we'd need 10 moles of this because it's a 1-to-1 ratio. We have 0.5, we need 0.5, but we only have 0.3. What does that mean? That means this is the limiting reactant, and this is excess. So all of our baking soda will react. It will be used up. All of the limiting reactant gets used up. There will be some vinegar, acetic acid left over. Now the question is about the carbon dioxide. How much carbon dioxide will we get? Well, according to the equation, for every 1 mole of this that reacts, 1 mole of this is created. But only 0.3 moles of this reacted, so we will get 0.3 moles of this produced. Because the limit is 0.3 moles, that means we will get 0.3 moles over here. All right, next issue. Now we need to find the pressure inside the 2-liter bottle. Let's do a little sketch here. Draw a 2-liter bottle. Terrible drawing, I'm sorry. What's in it to begin with? To begin with, we have 500 milliliters of 1 molar acetic acid. It's about like this. So right there is 500 milliliters, 1 molar acetic acid. Now we're going to have to make an assumption right here, or else this gets too complicated. We're going to assume that when we dump 25 grams of baking soda powder in here, that the water level does not rise. And it wouldn't much, but we're just going to have to make that assumption to keep from having to do some more complicated calculations. So we're going to say that 25 grams of baking soda are dumped in here. The level does not rise, and immediately we put a top on this. So you know that the reaction is quick. You've put baking soda and vinegar together. You know that it starts bubbling right away. So we've capped it, and carbon dioxide gas is now filling the airspace above the liquid. Well, if the whole bottle is 2 liters, and this down here is 500 milliliters, which is 0.5 of a liter, how much space is there from here up for the carbon dioxide to fill into? Here's half of a liter, 0.5 liters, 500 milliliters. The whole thing's 2 liters, so the gas space, the air space, is 1.5 liters. All right? So now we turn to our ideal gas law. PV equals nRT. We know R. It's 0.0821. It's always 0.0821 as long as we put the temperature in Kelvin, the volume in liters, and the pressure in atmospheres. So, how many moles of carbon dioxide gas are we putting into the airspace of this bottle? The answer is 0.3. What is the temperature, considering that it's 80.6 Fahrenheit? Well, first you change Fahrenheit to Celsius. 80.2, you subtract 32, you see what that is, and you divide it by 1.8. I think I did, yeah, that's fine. That's not what I was shooting for. Anyway, I'm going to round this off to 26. Let's round that to 27. That's what I was shooting for. I don't know how I messed that up. So we're going to call this 27 degrees Celsius. Then to change that to Kelvin, we'll add 273. So we get 299.66. We're going to round it off. We're going to call it, that's what I was trying to get, was to make this a nice even 300 Kelvin. I don't know, I goofed somewhere. 300 Kelvin, that's what I meant for it to be. Do what I'm thinking, not what I actually write down, okay? Read my mind, right? Okay, next, the volume. How much space is this 0.3 moles of carbon dioxide gas going into? It's all this space here above the liquid. It's 1.5 liters. And so what is the pressure? All right, so we've got to take this times this times this and divide by the 1.5 to isolate the P. So 300 times 0.0821 times 0.3 equals 7.389. We're going to divide that by 1.5. We're going to get a pressure of 4.926. I'm just going to call it 4.9. So pressure equals 4.9 atmospheres. Now that's 4.9 atmospheres higher than the pressure when the cap was off. When the cap was off, the outside pressure was what was in there, and it is 29.81 inches of mercury, which is just a little below 29.92 inches of mercury. For all practical purposes, it's still 1 atmosphere. But by capping it and letting that carbon dioxide gas build up in that space, the pressure goes up 4.9 atmospheres higher than that. It's a gauge pressure of 4.9, a total pressure of 5.9. Okay, next question. What is the density of that carbon dioxide gas? Let's find the density of the carbon dioxide gas in that bottle. All right, so density is mass over volume. How much carbon dioxide gas is in that bottle? It's 0.3 moles. Okay, but we need mass. How do we get from moles to mass? I can find the right flow chart to show you and remind you. We know how many moles, 0.3 moles. How do we get that to mass? We multiply by the molar mass to find the mass. So moles, 0.3 times the molar mass. Okay, if we add this up, 12 and 2/16 adds up to 44 grams per mole. 0.3 moles times 44 grams per mole. That's going to be, I believe, 13.2, I think. 44 times 0.3, 13.2 grams. Notice when you multiply moles times grams over moles, the moles will cancel out. So our density is our mass of 13.2 grams over the volume, which is the space where that carbon dioxide is located, which again is the space above the liquid. So it's 1.5, and 13.2 divided by 1.5 is 8.8 grams per liter. So that is the density of the carbon dioxide in this bottle. What if we had allowed the carbon dioxide to escape? It would have spread out. How big could it have gotten? What could its volume have been if it wasn't contained in that bottle? In that case, we would have done this. We would have said that the 0.3 moles, with R being 0.0821 and the temperature being 300, would have spread out to what volume at the pressure in the atmosphere at that moment. Now here's where I changed my mind and said we're going to go back and use this. Now, like I said, this is going to be really close to 1. And for a reminder, when we say 29.81 inches of mercury equals blank atmospheres, we're going to underline this. We're going to write the standard pressure down here, which is 29.92. We're going to write standard pressure in atmospheres down here, which is 1. We're going to try to find this X. So we're going to cross multiply. And what we end up with is 29.81 divided by 29.92, 0.996. So for all practical purposes, it's still 1. 996 thousandths of 1. I'm just going to leave it as 1. I'm going to say that pressure's 1. If you want to put 0.996 here instead of 1, knock yourself out. I don't think you're going to find a significant difference. So let's see what volume it would have taken up if it were allowed to expand out. So we get 0.3 times 0.0821 times 300, and that gets divided by this 1. So the volume now is 7.389. All right, so our density is the mass, which is still 13.2. That's 0.3 moles of carbon dioxide is 13.2 grams, no matter what. But it's over a much larger space now of, I'm going to round that off and call it 7.4. It was 7.389. So we're going to say 7.4. So 13.2 divided by 7.4 is only 1.78, or 1 point, rounded off, 1.8 grams per liter. Okay, so what's the point here? We produce 0.3 moles of carbon dioxide by this reaction, no matter what. If we cap it up inside the bottle, then the pressure inside the bottle goes up to nearly 5 atmospheres above the normal atmospheric pressure that's in there. And we are forcing those carbon dioxide molecules to stay in this little confined space, so they become more dense at 8.8 grams per liter. However, if we don't cap the bottle up and the pressure on the gas is 29.81 inches of mercury, that's outside the bottle, and it'll go through the opening to the inside as well, then that CO2 can escape and spread out and achieve a density of only 1.8 grams per liter. Okay, so wow, lots of stuff right here in this one page in 21 minutes. So a lot of review here and a couple of new concepts as well. So hope you got it.